Hello everyone, welcome back. If you are new, this is a new series that we have started in which we are trying to dissect segment trees from scratch. In the previous 8 videos in this series, we have discussed how to build segment trees, how to do point updates, how to do range queries, and the entire complexity analysis along with their proofs with the entire code walkthrough. We then solved the problems of various kinds and various difficulties in this series. And in the previous few videos, we have discussed about how to do binary search on a segment tree. Like we have discussed how segment trees node is actually looking like binary search and how we can utilize that to perform binary search directly on segment trees. So everything that we have discussed is being summarized in this particular Google Doc, bit.ly/segment trees. If you are new, you can watch videos, and I also added more practice problems so that you can practice and strengthen your understanding about segment tree. Doesn't matter if you are new or if you already know segment tree. I am very sure that if you follow this series, you will be able to learn and strengthen your understanding of segment tree. So the next few videos in this series will be very exciting. We will be discussing about merge sort tree starting this video, and then comes processing segment trees, which is a very good data structure to answer various queries. So let's start this video with merge sort tree, or rather the basic understanding of merge sort tree. So we'll first discuss why merge sort tree exists, because if you don't understand why a data structure exists, you will not be able to apply the data structure in any new kind of problem that you encounter. So we'll understand why it exists, what kind of problem or what class of problem that it solves, and then we'll actually go over how to build it, how to query it, and so on and so forth. So with that, let's start. This is how a usual segment trees look like. We have seen this picture a lot of times in this series. So just to summarize, we have an array. Each of these elements are present in the leaf of the segment tree, and all other nodes denote some property of everything below. So for example, let's say this node denotes everything in the range 0 to 3. So it will denote some property in the range 0 to 3. In this particular problem, or in this particular example, this denote the sum in the range 0 to 3, right? So if you sum them all up, you will get 8. So that's what this particular node denotes. So this is how you will now how usual segment tree look like, and this is the time complexity of different operations like building segment tree order n, range query order log n, point address order log n. Now, what exactly is the limitation of this data structure? Notice that you have stored 8 here, right? So you actually lose the context what all elements were there that contributes or that actually sums up to 8. You only store sum, and you lose context of each of the elements that is there. So we lose context that 1 plus 4 plus 2 plus 1 actually contributes to 8, right? And because of this, you actually lose a very important thing. Basically, you can't apply any algorithm that you know can be applied on an array, because you don't have the array itself, right? You just have a single number. So any algorithm that you could have applied on an array, you can't apply it now. There are various examples. Let's say in an array, you can easily count the number of elements smaller or greater than a particular number x. Similarly, in a given array, you can find out the sum of all the elements which are smaller or greater than equals to x. And similarly, you can find out the first element which is greater than x, and so on and so forth. So there are various things that you can apply on a single array, but if each of these things, you lost the capability of doing any of these things because you actually lose the context of what elements constitutes this particular value, right? Now that's the limitation that we are trying to solve. Now some of you might be thinking that, okay, let's say if we are able to answer this query for this particular node. Let's say we know that, let's take this example itself. Find the first element which are greater than x. So let's say you know how to answer the first element greater than equal to 5 in this particular node. So some of you thinking that how does it matter? If we are able to answer this here, how will we able to answer it in any random range? Let's say in the range 1 to 5, because 1 to 5 is not represented in any of the single node, right? So the answer is simple. It is very similar to how you do range sum in any other range. So you know how to answer a particular query for a single node. Now what you need to understand is how to merge the answer for two nodes. So if you have these two things, you will be able to answer any query in any given range. So let's say you know how to find out the number of elements greater than 5 in this particular range or in all the nodes. Now you somehow figure out that okay, I can just merge the value of this node and this node uh, by doing something. Let's say by doing simple addition, you can actually figure out the same thing, number of elements greater than equals to 5 in any range, let's say in 1 to 5, right? Because you know this range will constitute of some nodes, and you know what is the answer for each of these nodes, and you also know how to merge these nodes, right? So that's where, if we have every element, or if we have the entire array that constitutes this 8, then we can actually have the capability of answering everything that we can do in an array, right? So that's where merge sort tree would help. So hope you understand what the problem statement is and what merge sort tree is solving. So the structure is very simple. Structurally, it looks very similar to segment tree. It's just that instead of storing a single property, you are storing everything. That's it. So let's say this is the array again, 142123004. This array will still be represented in the leaf nodes, right? Now each of the above nodes, instead of maintaining a single property, they will maintain the elements itself. So it says okay, 1 to this 0 to 1 has 1 and 4. Similarly to 2 to 3 has 2 and 1, and so on and so forth. Now once you have the array, you can apply any algorithm that you know can be applied on an array and figure out or figure out or answer any queries that you can answer in a simple array. So whatever we have seen before, all of these can be done now with just maintaining this kind of structure. Now before going ahead and understanding how we will answer each of those queries, let's first try to understand the structure itself, how to build this structure, and what is the time and space complexity to build this structure, right? So there are, like, what exactly we are doing, we are maintaining every element in a range in a single node. So previously the single node contains a single integer, let's say x. Now this single node will not contain a single integer, instead a list of integers, right? That's the difference. So how many, or first of all, what's the space complexity of storing this? I would strongly encourage you to pause the video and try to think about the space complexity of storing this data structure by yourself, because that, if you have followed along this series, I am very sure you will be able to answer it. So hope you thought about it. The actual space requirement is order n log n. Now why order n log n? Let's think about it. So how many, or what is the depth of this segment tree? Depth of this segment tree is log n, right? So basically we have log n levels. Now what's happening in each of these levels? In each of these levels, we have broken 0 to n in some independent ranges. For example, in this particular case, we have broken 0 to 7 into 0 to 3 and 4 to 7. Similarly, we have broken 0 to 7 into 4 ranges in this particular level, right? 0 to 1, 2 to 3, 4 to 5, and 6 to 7, right? So every level actually breaks the range into independent. Notice the word independent. Independent ranges at a given level. Now, what does it mean? It means that if you just combine this entire array, you will be getting the original array, right? So number of elements you are storing at each level is just order n. Let's say you don't maintain a static array, instead you maintain a vector that will grow as per your demand. You know that total for a single level, you will be storing order n number of elements, or exactly n number of elements. Similarly, in this last level as well, you are storing exactly n number of elements. So you are storing n number of elements at each level, and we already know the number of levels is log n. How? Because each of this we are dividing into exactly half and then further dividing half. So basically, if you don't understand this particular part, I would encourage you to watch the first video in this series. I will link that in somewhere in the top right eye section or description down below. If you don't understand the complexity of query or this, do check that out first. So because of login levels and each level having n nodes, the number of or the space complexity of this entire of storing this entire structure is order n log n. Now notice that this n log n is most of the time possible because n most of the time is somewhere around 1 million or a point 1 million or so. So complexity is well under control, or space complexity is well under control. Now what's the time complexity? Again, if you think about it naively, time complexity is also n log n. Why? Because how will you build this first of all? So if you remember the first video, we have built this entire segment tree by using recursion, right? We said that okay, we want to build the segment tree for the range 0 to 7. I will say first build the segment tree for the range 0 to 3, then build the segment tree for the range 4 to 7. Now once you have these two trees built out, then just merge these two tree and get a segment tree for 0 to 7. Now let's say you have already built the segment tree, right? Now let's say you have already built this particular tree as well. Now what about this merging part? Previously merging part was just order one operation, but now merging part is not order one. Instead it is somewhere, if you think about it, it is somewhere in the range order n, right? So because you have this n number of elements here, but again this order n is actually across a single level. So if you think about it, uh, across all the levels, you will be actually iterating over single element or exactly once, right? Because that's what you are doing. So because of this, the time complexity of building this entire data structure is also n log n, right? Now let's quickly look at the pseudocode. The pseudocode is exactly similar to how we have built the segment tree initially. So notice that we have used recursion again. So this LRI, L2R, if you remember, we have discussed many times, L2R denotes this particular range, which denotes what is the range uh, current node denotes, and I is the range, I is the index of the array in which we are storing segment tree. Just to uh, remind you, we instead of storing segment tree in a tree fashion with left and right child pointers, we are storing segment tree in a array, just to avoid the complexity that comes with the pointers, right? So this I denotes the index at which this particular range will be stored. So the 0 to 7 will always be stored at the first index, and then the children will be stored at, let's say this is the ith index, children will be stored at I cross 2 plus 1 and I cross 2 plus 2, right? So this is just the usual trick that you do while implementing heap sort. Now, uh, the base case we have handled that if it is a leaf, we know that leaf will contain just a single element. So we just maintained tree of I to be array of L. Now, previously this array was a single dimension array, but now this array would be a two-dimensional array where each of these index will have a array of its own, and they will be of different sizes as well. So some of them will have one element, some of them will have more elements, and so on and so forth, right? Now, after building the left and right segment trees, we will just build the current segment tree by merging the left and right trees, right? So this merge function previously was just add the values of the left and the right child, but now it is not just addition. Instead it will iterate over all the elements here, iterate over all the elements here, and then combine the array. And then build this tree of I array, right? So this entire thing would work in just order and log n. We have already discussed the reason. So now let's go to the slightly harder part, which is query. So let's say again you have to query something in this particular data structure. How you will do that? Let's take an example of 0 to 6. So you have to query something in the range 0 to 6. Now that something could be anything that we have discussed previously, like any property of an array. Let's say in this particular example, we want to find out the number of elements greater than 5, let's say in the range 0 to 5, 0 to 6. Now how will you do that? Again, you have to query something in the range 0 to 6. You have to first figure out which all nodes contributes to this particular query, right? Now how you will do that? You will say, okay, the first node is 0 to 7. So is 0 to 7 completely overlapping with 0 to 6? Answer is no. So you will go in both left and right child, right? Now again, you let's say you start here left, you go first left. So in this case, left will have 0 to 3. Now is 0 to 3 completely overlapping? Answer is yes, 0 to 3 is completely overlapping. So you will say that, okay, I will not go further down and I will include this entire node, right? So you have include this entire node. Now let's say you go right, you say, okay, 4 to 7, is 4 to 7 completely in this particular range? Answer is no. So you go in both the direction, left and right. Now finally when you go left, you will see, okay, 4 to 5, 4 to 5 is completely inside this range, so you will pick this entire node itself, right? Now when you go right again, you will see 6 to 7 is not in this entire range. You will again go left and right. Once you go left, you will see, okay, 6 to 6 is completely in this range, so you will select this particular node, right? And this is completely outside this range, so you will not go further as well, and you will stop your search here. So in total we have three ranges that we need to, or that will contribute to the query 0 to 6, right? Now this whatever we have done so far will take order log n time, or in other words, we take order log n time to figure out how many ranges are there, and there will be at most log n ranges as well. If you have doubts in any of these things that we have just discussed, again strongly encourage you to watch the first video in the series, in which we have discussed how exactly range query works and how this login factor is coming in. Now once you know that you will have login nodes, what exactly you will do? Remember the query was find me, let's say everything which is greater than equals to 5, or find me the first node which is greater than equals to 5. So in this particular case, you will maintain something here, like either you will sort the array or you will maintain a set or any other data structure here, right? So anything that you do will have some complexity attached to it, right? So let's say you are doing like you are maintaining a set here for some reason. So doing a query in set will take order login time, and now you are doing the same query in these three nodes and merging them as well. So let's forget about merging part. Let's say you know the answer for to calculate the answer for this particular node, you require login time. Similarly, to calculate the answer for this particular node, you require login time, and similarly for this one, login time. So you have login nodes, and for each of these nodes you require login time because of the data structure that you have maintained. So for each of these login nodes you require another login time to actually query the actual data structure that we have maintained here. So the entire complexity of uh, doing a range query in this merge sort tree is order log square n, right? So it again, this login factor actually depends on what data structure you have here. If you're just maintaining an array or suffix sum or prefix sum, this will go away, right? Now, uh, now last thing is update. Update is also very straightforward here. So let's just discuss about updates here as well. So let's say you have to update a particular value, let's say 0th index to the value 6, right? Again, we haven't discussed range updates yet. I have received multiple requests to make a video on range updates, but before diving into that particular piece, I wanted to make sure that we cover everything that is possible with point updates, right? So let's see how point updates works here. So let's say you have to update this particular number to 5, right? Now what will change? Again, you will directly encounter login number of nodes in this entire journey, right? Because the number of levels is login, right? Now, once you change it to 5, you have to do the same for everything where you have stored this particular 4, right? So what, or sorry, where you have actually stored this particular one, right? Now, what exactly will it take to actually replace everything with 1? Now it depends on what data structure you have maintained in each of the nodes. Again, let's take the previous example where you are maintaining set. So if you are maintaining a set at each of these nodes, then to actually remove an element and update an element, you would require login time, right? So in essence, you are traversing login number of nodes. Now for each of these nodes, you have to update each of these nodes. Now updating each of these nodes will depend on what data structure you have maintained. And if you have maintained a data structure that takes login time, then updating uh, or doing a point update will also take log square n time in merge sort tree, right? So hope the entire thing is clear. Just to contrast it with the original segment tree, building the segment tree requires order n time in the usual segment tree part, but now we require n log n time to build the merge sort tree, right? Now querying doing a range query is log n time. Now doing the range query in merge sort tree depends on order log n time multiplied by the complexity of the data structure that you are maintaining at each nodes, right? And similarly for point updates, login time multiplied by the complexity of data structure that you are maintaining at each nodes, right? So one more thing, I think this is also true that you will it will be also multiplied with the complexity of data structure this that you are maintaining at each of these nodes. And I forgot that basically when you are building this entire thing, let's say you are maintaining a set here, so you are inserting every elements one by one to the set. So inserting one element to the set requires login time, so you are inserting n number of elements across this level. So total insertion would take order n log n time. So the complexity is not order n log n, rather you can say they are order n log n elements, or space complexity is still order n log n, but time complexity is order n log square n. Or it depends on what's the strategy or data structure that you're using at each of these nodes, right? So hope this entire thing is clear. Now let's revisit this particular thing. Now you have addressed the limitation of the original segment tree, and because you have addressed that, you can actually solve for each of these scenarios by yourself. Now let's say you have to find out the first element greater than x. So what you can simply do, you can simply come here, see the first node which actually contributes to this range. So in this particular case, this will be the first node that contributes to the range 0 to 6. You will go to the first node and just do a query that, okay, find me the first element greater than equals to x. You will do the same for everything. Like for this node, let's say you want to answer this query for this particular range, and we have already seen that this particular range is constituted of this and this. So you will go to each of these, figure out the first element which is greater than x in each of these, and take the minimum across all three. That will be the first element which is greater than x in the range 0 to 6, right? So hope this particular thing makes sense. Basically, instead of maintaining this particular thing, you will be maintaining a sorted array. So either you can maintain a set, or you can simply maintain a sorted array, because sorting the entire array would require the same time, right? So you are now able to answer this query efficiently in order n log n, like in order n log square n, right? Similarly, you can answer this one as well. You can just maintain a prefix sum and return the prefix sum for this particular, by doing a binary search over here, and sum all the prefix sum from all the contributed node, and that will be your answer. So in the next few videos, we'll be looking at some of the problems that utilizes this merge sort tree concept. I would strongly encourage you to try the first problem by yourself. In the next video, you're looking at the exact solution of this particular problem and the code as well. So again, one more thing that you can try till the next video is watch this particular YouTube video. So this one was uploaded last week as a part of last week's lead code contest, and this is a very good example of when merge sort tree can come handy. So if you have time, I would encourage you to watch this particular video as well. So with that, I will stop here. If you have any doubts in the particular video or anything that you have discussed till now, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.